All right, let's go ahead and get started. So today's going to be the last lecture on this module on motion planning. So just to remind you of where we left off in the previous lecture, so we started discussing motion planning with dynamics constraints. So our first pass at the RRT algorithm, we didn't take into account constraints that your robotic system might have in terms of how it can move. So that's what we tried to fix, or started trying to fix in the previous lecture. And more specifically, we discussed a pretty broad class of systems which are known as differentially flat systems. So we looked at the planar quadrotor as an example of a differentially flat system, and then I mentioned a couple of other systems as well. So the full 3D quadrotor dynamics also satisfy this property of differential flatness. I think the general kind of definition of differential flatness might look a bit abstract and intimidating, so I just want to highlight the main idea, the main intuition behind flatness. So basically what differential flatness allows you to do is we can specify any trajectory. So I guess it's caveated with any sufficiently smooth trajectory in the flat output space. So whatever the flat output space happens to be for your system, for the planar quadrotor, this was the XY position of the center of mass. For the full 3D quadrotor, I mentioned that the flat output space is X, Y, Z, and yaw. In general, the dimension of your flat output space is going to be the same as the number of control inputs that your system has. So yeah, we can specify, so if your system is differentially flat, it means that we can specify any sufficiently smooth trajectory in the flat output space. And we can do two things. So we can recover a control input trajectory and that's going to make the flat outputs do exactly what you specified. And then moreover, we can recover the full state trajectory. So again, for the planar quadrotor, if you come to me with a sufficiently smooth trajectory for the center of mass, I can give you a control input trajectory that's going to make the center of mass do what you specified, and then moreover, I can tell you exactly what the full state is going to do. So we don't have direct control of the full state, right? I'm not saying that you can come to me with any trajectory for the full state of the system, and I'll give you a control input sequence that's going to make the full state do that. I'm just saying if you come to me with a center of mass trajectory, then I can get the system to follow that center of mass trajectory. The other states might do something wacky and like weird. We don't have direct control over it, but we can directly control the center of mass. So that's basically what differential flatness is giving us. And while extremely, or like relatively broad, like not all systems are differentially flat, or not all systems are known to be differentially flat. So the plan for today is to discuss motion planning, with dynamics constraints, for systems that are not known to be differentially flat. or I can say systems that are not necessarily differentially flat. So that's going to be, I guess, maybe half of the lecture or so. The second thing we're going to do today to wrap up our discussion on motion planning is to relax this assumption that we've made, which is that we can follow any trajectory exactly, like without any errors. Of course, in practice, we're not going to be able to do that. There's going to be some uncertainty in the dynamics, some external disturbances, like wind gusts that make the drone kind of move away from whatever trajectory it's trying to follow. So we're going to discuss some techniques for doing feedback control for trajectory tracking. So this is slightly different from our first kind of discussion on feedback control, which was targeted at making some equilibrium state, like the hovering state, asymptotically stable. What we're going to try to do here is not try to get the system to a particular like fixed state, but rather to track a trajectory in state space. So yeah, that's the plan. So I guess let's start with the first part. I'm just going to switch to the slides here. Question?
So for when we're recovering the control trajectory,
Yeah.
do we assume that we can change our controls like relatively quickly, or do we like some time like T star?
Yeah.
Because like I assume we can't always change our input. Like.
Yeah, that's a good question. I guess let me just repeat the question in case you couldn't hear it at the back. So the question is, do we assume that we can instantaneously change our control inputs, or do we assume that there might be some lag in how quickly you can change your control inputs? So here we're assuming that you can instantaneously choose control inputs at any time. So you can switch between one control input and another instantaneously. The way to modify, so I guess one kind of trick you can do is change your control inputs such that it captures the difference in control input from time to time. And that gives you a way of like potentially saying that I don't want to change my control inputs, like my original control inputs, like that much from time to time. If you put a cost on the new control input, which is the change in the original control input. So there's like tricks you can play like that, which allow you to bake in some of those like real world constraints. But yeah, for now, anytime we say control input, we're just going to assume that you can like set the value of the control input to whatever you want at any time. Yep. Good. Okay, let me maybe lower the lights a bit. All right, so what we're going to do, the general kind of approach here we're going to take to bake in dynamics constraints into our motion planning algorithms will be to start with the RRT algorithm and modify it to handle dynamics constraints. So I guess just as a quick reminder of the RRT algorithm, this is an iterative algorithm that operates in the configuration space. So we're growing a tree in the configuration space of your system. So for a planar quadrotor, the configuration space is x, y, theta. For a full 3D quadrotor, it's x, y, z, roll, pitch, yaw. So not including the kind of velocity terms. And at every iteration, you sample some random configuration from your configuration space. You look at the closest point in the existing tree that you're growing iteratively, and then you try to extend the tree towards the point that you've sampled. And one variation that we discussed in the previous lecture is instead of growing the tree in the configuration space, you grow the tree in the flat output space. And in that case, differential flatness gives you a way of doing that extension operation kind of exactly while obeying the dynamics of your system. But yeah, today we're going to focus on systems that are not necessarily differentially flat. So the question is, how can we modify something like the RRT algorithm to take into account some non-trivial dynamics constraints? So this is our general form of dynamics, right? We can always take some second-order differential equations that you get from F equals ma, and write it in this first order form. So hopefully everyone is comfortable with this form now. So x dot equals f of x and u. X is the state. So these are the configuration variables and the kind of derivative terms, and the u is the control input. So the main idea that we're going to try to pursue is to, instead of constructing the RRT in the configuration space, we're going to construct the RRT in the state space of the system, so the space that X lives in. So here's one idea. So we're going to, I guess, propose some algorithms. We're going to see whether or not they work well, and then we're going to try to improve our algorithm. So this is kind of idea number one. So here's idea number one. So on each iteration of the RRT algorithm, what we're going to do is randomly sample a state from the existing tree. So you initialize the tree with the starting state. We're going to call that XA. So in the first iteration, you just sample that state. In general, you sample some random configuration from the existing tree. So this is different from the RRT algorithm. Right, so the standard RRT algorithm, you sample some random configuration from your configuration space, then you find the closest point in the tree. Here we're saying we're just going to randomly sample some point from the existing tree. We're then going to randomly select a control input, which we're going to call urand, and we're basically just going to apply that random control input for some small amount of time, which we call dt. Right, so what this results in is you start from this random state, xrand, and then you just integrate your dynamics forwards. You just see where the system ends up if you apply this random control input for a small period of time. And you call that state that you end up in when you apply that control input for a time of delta t, you call that xs. And then you check whether this state, xs, is in collision or not with any obstacles. If it isn't in collision, then you throw away this iteration. You kind of revert back to your tree before this iteration. If it is not in collision, then you add that to the tree. And then I guess if you're close enough to the goal, then you just terminate the algorithm. So yeah, this has a different structure from the RRT algorithm. Right, so we're doing things in a different way. We're like randomly sampling points in the tree, randomly selecting control inputs, and then growing the tree that way. The kind of benefit of this, or one, I guess, nice feature of this algorithm, is that the trajectory that you get out at the end of the process is guaranteed to be dynamically feasible, because we're like essentially by construction, right? Like we're choosing control inputs and then ending up at states that you would end up in if you apply that control input, and then iteratively growing the tree that way. So if you just apply these control inputs, then you're guaranteed to go to the state xs from the xrand state. I guess questions on this algorithm, just the structure of the algorithm? Okay, does someone have intuition for whether or not this is going to work well? Or any, I guess any thoughts on, is this, maybe we can start with a concrete question, like is this going to find a trajectory, if a trajectory exists from start to finish in the state space, is it going to find a trajectory? Go ahead.
I just have a question about this, like, yeah, actually might have
Sure.
Is there any like boundaries on the control input?
Yeah, good question. So this algorithm actually allows you to specify constraints on the control input. So for example, for a quadrotor, there might be a bound on the thrust that you can produce. And typically, propellers only spin in one direction, so you can't produce like negative thrust. So 0 is a lower bound typically on the thrust, and then there's some upper bound depending on how quickly the propellers can move. And yeah, you can modify this algorithm to take those into account. Basically, the control input that you sample, like urand, you sample it just from the allowable set of control inputs. Question?
It also doesn't seem like you explore it, seems like you end up staying in the same
Yep.
place.
Yes, yeah, so that's exactly right. So it turns out that the good news is that one can show that this algorithm is probabilistically complete, in the sense that if there is a way to get from the start state to the goal state, or close to the goal state, this algorithm will find it or the probability that the algorithm finds it converges to 1 as the number of iterations goes to infinity. But it doesn't actually work well in practice. So the number of iterations, exactly as you were saying, the number of iterations that you need to find the path can be very, very large. And this is what you get when you run this algorithm for some number of iterations. It's basically just a jumble, right? It's just like a jumble like around the starting location. The starting location here is around 0, 0. And it's kind of just doing this like random walk, Brownian motion if you're familiar with that. And it is exploring, but very, very slowly. So you're just going to get like a jumble that keeps growing very slowly over time. Eventually, that jumble is going to grow to encompass something that's close to the goal state, but that's going to be very slow. All right, yeah, I guess questions on this? So in some sense, this shows the weakness of probabilistic completeness, right? Like one could say, oh, like my algorithm is like probabilistic complete. Wow, like that's amazing. But yeah, it turns out you can come up with like pretty silly algorithms that are also probabilistically complete, but don't work well in practice. So probabilistic completeness is a nice like property to have for an algorithm. Like it should at least be probabilistically complete, but just because you have probabilistic completeness doesn't mean that it's going to work particularly well in practice. Okay, so yeah, I guess let's try to modify the RRT again to fix this problem. So we need something basically that promotes exploration, so similar to the RRT. And the key kind of step in the algorithm that in the RRT algorithm that promotes exploration is the fact that we're randomly sampling essentially some like direction to explore in from the kind of like boundary of the tree. So we're randomly sampling some configuration, finding the closest point in the tree, and then expanding the tree. So that's kind of like growing the horizon of the tree, the boundary of the tree, if you like, in directions that have not been explored so far. So the idea with this kind of second iteration of the RRT that takes into account dynamics constraints is going to be to keep the structure of the RRT algorithm essentially the same. The only thing we're going to change is how we do the extension operation. And so that's going to basically allow us to explore while still allowing us to satisfy the dynamics constraints that your robotic system has. Okay, so here's the second kind of version of our algorithm. So again, we're going to initialize the tree with just the starting state xa. At each iteration, we're going to randomly sample a state, as in the usual kind of RRT. Usual RRT, we do the sampling in the configuration space. Here, we're sampling in the state space. But then this is not from the existing tree, right? We're just randomly sampling some state that's not necessarily part of the tree right now. We find the nearest vertex, the nearest state in the existing tree, and then we're going to somehow have to grow the tree from x near to x rand. And that's the tricky part, right? So if we assume that your robot can execute any trajectory, then we could just say, like, connect x rand to x near with just a line segment. But because your robotic system has some dynamics constraints, you can't just like follow a line segment in state space, as we saw with the car example, for instance, or the planar quadrotor like cannot just like translate sideways. So here's one idea. So we can sample a number of control inputs and basically see which one gets you closest to x rand. Right. So ideally, we want to go in the direction of x rand exactly. Maybe we're not going to be able to do exactly that. So a proxy for moving towards x rand exactly is to sample, let's say, 100 control inputs or some like fixed number of control inputs, and see which one gets you closest to x rand. Let's say just in terms of Euclidean distance. So when you start from x near, you apply some control input, you see where it gets you, and you try a lot of different control inputs, which you apply for some small amount of time, which I'm calling here delta t. And then you continue as usual with the RRT algorithm. So you see where you end up. You check whether that state is in collision. If it is in collision, then you throw it away. If it's not in collision, then you keep it and you grow the tree like that. Yeah, so I guess questions on this version of the algorithm? Go ahead.
Is there sort of an optimal number of control inputs to choose? Because like, you could end up doing so much of one iteration
Yeah.
than your output.
Yeah, so there's a kind of trade-off here. So there's no kind of analytical optimal like solution. It's something that you have to figure out by trial and error for your specific problem. But yeah, if you sample too few control inputs, then the likelihood that you're going to make progress towards XRAND is low. If you sample too many control inputs, then, like you said, each iteration is going to be computationally expensive, and so that might slow things down. So intuitively, there's going to be some sweet spot like in the middle, but I don't know of a kind of principled way of finding that. Yeah, just like trial and error for your particular problem. Question?
Yeah, I was wondering how the sampling is taking place. So, like, is there some efficient algorithm for sampling, or
Yeah.
is it just random?
Yes, good. So in this version, I'm just saying like uniformly random. But yeah, you can make this more clever by like biasing the control input, like sampling in a specific way. I'll say a little bit more about that in a couple of slides, but that's definitely, if you know how to do that for your system, then you should. Yeah. Go ahead.
Are we still considering obstacles?
Yes, yeah, we are still considering obstacles. Maybe let me just sketch out just this algorithm, maybe one iteration of it. So let's say these are a couple of obstacles. You can think of these obstacles as living in the state space of the system. Like not necessarily, you don't have to like construct these explicitly in state space, but just, yeah, just for the purpose of drawing pictures, imagine that these are obstacles in state space. So yeah, we have some existing tree, let's say that looks like this. So what we're doing is sampling some random state XRAND. We're finding the closest point on the tree, which is this point, and then we're sampling some number of control inputs. So let's say this is one control input, this is another one, maybe this is another one, this is one. And if you apply the control inputs for some small amount of time, delta t, then your state is going to evolve in a particular way. So it's not going to be a line segment, right? Your state is going to obey whatever differential equations like x equals f of x u that describe your dynamics. And so you're going to have like a little like trajectory that goes from this state to some new state. And then what I'm saying is like you pick the control input that allows you to make the most progress towards the XRAND state, and then you grow the tree. So yeah, the step where the obstacles come in is when you extend the tree in these different directions, you can do collision checking. So you can check whether this state is in collision or not. If it's not in collision, then you keep it. If it is in collision, then you can just throw it away. There's things kind of that are intermediate that you could do. So if this state is in collision, the one that makes you make the most amount of progress towards the random state that you sample, if that state is in collision, then maybe you throw that away, but then you look at the next state, or sorry, the next control input that makes you make the most progress towards XRAND. If that's not in collision, then you keep that. If it is in collision, you can keep kind of checking all, like you've done all this work in terms of sampling different control inputs, so you can check each of them and find the one that's closest to XRAND that's not in collision. Question?
I think like for most systems we work with, we have the time gradients and also gradients in the control inputs.
Yes.
Shouldn't there be a way to analytically find the
Yep.
control?
Yes, yeah, good. That's going to be, I guess, idea number 3 is going to use that. So yeah, instead of just like randomly sampling control inputs and seeing which one gets you close to the goal, so no, not the goal, close to XRAND, yeah, you can be a little bit more clever and optimize a control input. Yeah, I'll get to that on a couple of slides. Question?
Just what about this algorithm tells us that sampling the control inputs isn't going to be
be like a line segment when you're drawing?
Yeah, so that depends on the dynamics of the system. So if you just have some arbitrary dynamics, x dot equals f of x and u, the trajectory that you end up following, so whether it's a line segment or not, just depends on the exact form of the dynamics, so the exact form of f. So I guess for a planar quadrotor, imagine that it's in some like tilted configuration. If you apply a constant control input for some short duration of time, it's kind of going to go like this, right? So it's not going to be a line segment, even in terms of center of mass. So the exact trajectory that you follow when you apply some control input for a short duration of time just depends on these dynamics that describe your system. So we're relying here, I guess I didn't mention this explicitly, but we're relying on being able to integrate the dynamics. And in general, if f is nonlinear, we cannot do that analytically, but you can use numerical techniques. So if you use like ODE45, for instance, or scipy.integrate is the Python version of that, to get these like kind of local trajectories that you get when you apply control inputs for the period delta t. Okay, other questions on this? Okay, so all right, so this algorithm I think can work reasonably well. It's definitely an improvement on our idea number one, and especially for systems that have a relatively small number of control inputs, so small dimensional control input space. What happens if your control input space is high dimensional is that if you just randomly sample a control input in a high dimensional space, the probability that one of those is going to result in progress towards this random state that you sampled, the probability is going to be low, right? So you're not going to make much progress if your control input space is high dimensional. Question?
What if, I'm forgetting the exact linear algebra, so what if you just like shrunk your component space down to like a couple dimensions?
Yeah.
And just sampled along those? And
Yeah.
then tried to find this linear algebra?
Yeah, so if you had some like subspace of the high dimensional control input space, if you can find such a subspace that allows you to make progress in many different directions in your state space, then you should do that. But it might not exist, right? For like a humanoid robot, like it's not clear whether there's some like low dimensional subspace of the control input space that's going to make the humanoid robot kind of do interesting things like explore in state space. Yeah. Okay. So another, I guess, bug or feature of this algorithm is that the algorithm is sensitive to how we define closest. Right. So what I was saying here is that you find the closest point in terms of the Euclidean distance, so the standard notion of distance, but that may not be the best choice. So I guess here's a example. Let me erase this. Some real-time feedback control. Yeah, so I guess here's an example. So this is with the car system that I sketched the previous time. So here's one pair of states. One state is the robot, let's say, has some fixed like velocity in the forward direction. The other state is where the center of mass is just like translated, and it's moving with the same like fixed velocity. Let's consider like another state, which is over here. So again, the velocity is fixed, just the position is changing. So I'll call this state 1, I'll call this state 2, and I'll call this state 3. And actually, I guess let me make it a bit more extreme, just to highlight the point. Okay, yeah, so these are our three states. So same fixed velocity for each one, just different locations. So in terms of Euclidean distance, so the standard notion of distance in the state space, I guess which of these pairs is the closest? So let's take like 1 maybe as the reference point. So is 2 closest to 1, or is, sorry, I drew 3, yeah, it wasn't meant to be a trick question, or is 3 closest to 1 in terms of Euclidean distance? Go ahead.
If you could move on all axes, 2 would be closer.
Yeah, so if you're just looking at the distance in the state space, then 2 is closest to 1 because the velocity components are the same for all 3, it's just the location is different, and 2 is closer in terms of location. But I guess intuitively, in terms of, if you think about the dynamics of the system, which of the states, or like, do you think like 3 is closer to 1, or is 2 closer to 1? Maybe let me rephrase the question a bit. So is it easier to get to 1 from 3, or is it easier to get to 1 from 2? So I see a show of hands. So it's easier to get to 1 from 3. And the reason is you can just go straight, right? So in a short amount of time, basically just by moving in the direction you're moving in, you can go from 3 to 1. Whereas going from 2 to 1 might require more effort, right? So you might, because you cannot move sideways, you have to do some potentially complicated maneuver to get from 2 to 1. So I guess, does that make sense? Questions? Yeah, go ahead.
So if you have a system with, say, 10 control inputs and 9 of them moved forward and backward, and only 1 of them had any impact on sideways motion, and you're sampling randomly, would it be, if you ever wanted to move sideways, it's likely most of the sampled random values you get would still move in only 1 direction? Yeah, exactly. Yeah, and so that's an argument for not using random sampling, or an argument for not using Euclidean distance as your notion of distance. So there are ways to modify the notion of distance to capture the dynamics of your system. So yeah, something that says 3 is closer to 1 than 2 is to 1. Yeah, I won't go into the details of how you define these, but I guess that the main point is that Euclidean distance is not necessarily the correct choice of distance when we're growing the RT. Another example, just to build more intuition, is if you have a pendulum. Let's say this is an inverted pendulum, and the velocity here is in this direction. So this is one pair of states. So the pendulum is at this angle or at this angle, but both kind of moving in the same direction. Or I guess this is slightly tricky to draw. Let me just extend the pendulum a bit. So the angle is the same, but the velocity is very different. So the velocity is in the other direction. So if you're moving in one direction, it's kind of the same thing as the car. So if you're moving in one direction, then even if you're slightly further away in terms of the angle, like 2 states that are moving in the same direction might be considered closer, even if they're not necessarily the closest in terms of Euclidean distance. So yeah, the Euclidean distance is not necessarily a good metric in the state space for defining how close 2 states are. So we thought about the pendulum or the car. And I won't go into this, but there are other metrics of closeness that one can derive based on the dynamics of the system, and then you can modify this algorithm in a pretty straightforward way. Instead of finding the closest point in terms of the Euclidean distance, you find the closest point in terms of some other distance that better captures the dynamics of your system. And basically, this can improve the efficiency with which a path is found. So the number of iterations that you need for the RT algorithm can be made to be smaller than if you were just using the Euclidean distance. Okay, here's idea number 3. So I think someone kind of already foreshadowed this. So again, we're going to keep the RT algorithm structure the same, but just change the extension operation. So we're going to do this by solving what's known as a boundary value problem. So the structure again is the same. So we sample some xrand, we find the closest point in the tree, x near, and then we're trying to kind of grow the tree in the direction of xrand. So what we can do is find or connect x near to xrand with a line segment, and then try to get towards some point on the line segment, which I'm calling xs here. So you might not be able to traverse that line segment exactly, right, because of the dynamics of the system, but maybe there's some short kind of sequence of control inputs you can apply that's going to take you from x near to xs. So yeah, I guess this is called a boundary value problem. The boundaries are fixed, like the starting and end configurations are fixed, and you want to find some control inputs that drive your system from x near to xs. This also goes by the name of trajectory optimization. So you can think of this as an optimization problem. Like I want to find a short sequence of control inputs that satisfies the constraint that my starting state is x near and my ending state is xs, maybe while minimizing the control effort you need to make your system do that. You can tackle this. Again, I'm not going to go into the details here. I just want to make you aware that these techniques exist. So we can tackle this using techniques from nonlinear optimization. And this is a pretty active area of research, like doing trajectory optimization for systems that have non-trivial dynamics. So yeah, I guess one question you might ask is, well, if we can just do that, if we can just solve this boundary value problem, like why do we even need the RRT, right? Like just solve a boundary value problem from your starting state to the end state. And yeah, if these techniques are so good, then there's no point even doing the RRT. You just solve a big trajectory optimization problem. Sometimes you can do that, like especially over relatively short periods of time. You can, in a single kind of shot, like one optimization problem, find some trajectory that goes from the starting state to the goal state, avoids obstacles. But yeah, this if you try to do this for a longer time horizon, then like these optimization algorithms get pretty computationally intensive or don't necessarily find good solutions. So they're particularly good over short time horizons. So if you can combine the structure of the RRT algorithm with this trajectory optimization step that's responsible just for local extensions of the tree, then that tends to work pretty well in practice. All right, yeah, I guess questions on this? Okay, so let me switch now back to the Blackboard. So basically, how do we deal with uncertainty or disturbances in the dynamics of your system? So far, in like all our discussions about motion planning, we've made this assumption, which is that we can exactly follow some trajectory that a motion planner gives us. But yeah, of course, this is not really true, right? So in practice, this assumption is violated for a couple of different reasons. So the first one is the exact initial condition. We write it like this: uncertainty. So you might have some uncertainty in the initial state of your system. So if you have a drone, maybe you don't know exactly where it's going to start off. So you've planned a trajectory assuming a particular starting state, but really in practice, so yeah, you made some plan that goes from A to B, But let's say your drone just starts off at a slightly different initial state. So that's one reason why you might not be able to exactly follow the trajectory that you planned. Or you might have some uncertainty in the dynamics. So for example, the physical parameters that you identified for your drone might not exactly capture the real system, or there might be external disturbances like wind gusts. So even if you start off following this trajectory exactly, maybe there's a wind gust that comes in and blows you away from the trajectory that you were trying to follow. So yeah, I guess this is where feedback control comes in. Is that better than last time?
Yeah.
Yeah? Okay, good. I'll use this chalk. Okay, good. So let's say we have, again, some dynamics. X dot equals f of x cubed, as usual in our standard first order kind of general form. And then suppose we have some trajectory that we're trying to follow. So, for example, found using like one of the variants of the RT algorithm that we described today that takes into account the dynamics of your system. So just pictorially, this is a trajectory in state space. So the trajectory I'm going to call x0. So it's a function of time, where time goes from 0 to capital T. And you have some control input sequence as well. So basically, if you start off at the initial state and you apply this control input sequence over the period 0 to capital T, then you follow this trajectory x0 of t. So the subscript 0 here refers to the fact that this is our nominal kind of reference trajectory. The parentheses is time. So this is x0 at time 0. This is x0 at time capital T. And just some point over here is x0 at some arbitrary time little t. And now, let's say at some time t, the true state of the system is not exactly where you want it to be. So if everything is going perfectly, your robot is going to be at this state, x0 of t. But in practice, like maybe you deviated a little bit, and then you ended up at some other state, which is just x of x at time t. Right, so the question is how can we basically get back to the trajectory that we're trying to track that came from a planning algorithm question.
Why would you want to get back to the exact same trajectory? Wouldn't you want to instead like make a new trajectory that?
Yeah, good. So you could also just replan entirely. So you could say, okay, I'm at this state. I want to get to some goal. I'm just going to resolve the planning problem. So there are, I guess, pros and cons. So if you haven't deviated that much from the trajectory you're trying to follow, then it might still make sense to keep trying to follow the trajectory you're trying to follow. You can replan. The challenge with replanning is that often that takes a fair bit of time. So doing that online, on board your system, like as it's like flying, can be computationally intensive. But yeah, that's definitely something you can do if it's computationally feasible. It makes sense to do that as well. Yeah. But yeah, I guess for now we're just gonna. I'll show you some like videos where that sort of thing happens. For now, let's just say we're trying to. We're like committed to a particular trajectory, and we're just gonna try to get back to it and not replan. Yeah, good question. Okay. So what we're gonna do is apply some feedback control, and we're gonna choose a particular like form of the feedback controller. So we'll apply a control input. Of the following form. So u, the control input at time t, is going to be the nominal control input that came from our trajectory planning, motion planning algorithm. That's this term over here, plus some matrix. This is the gain, GAIN matrix again, times x of t minus x0 of t. So yeah, this should look very familiar. This is like basically the same form as PD control, basically the same form as LQR when we were looking at stabilization. The only difference here is that everything is time varying, right? So we're not trying to get to some particular like fixed state. We're trying to follow a trajectory, so the state that we want to be at any given time is different than any given time question.
So is the nominal u just what you originally calculated?
Yes, yeah, the nominal u, the first term here, is whatever you originally calculated that makes you follow the trajectory, assuming you're exactly there and there's no disturbances. So yeah, if your state at time t is equal to the state that you want to be at, so if you're following the trajectory exactly, then this term is just 0, and so you continue applying the nominal control input. If this term is not 0, so if there's some deviation from the nominal trajectory, then you add in this correction term. And of course, what we're going to think about is how to find what this K matrix is. Question?
You already brought us up, but is U completely continuous in time? How is that?
Yes, so U is defined for every time, every point in time, 0 to capital T. It might have some structure, so I guess one of the versions of the algorithm I described today, you might end up with control inputs that look sort of like this. So maybe it's like piecewise constant, but it's defined for every point in time.
So most algorithms have like a certain interval where they're the same when they switch.
Yes, yeah, exactly, yeah. So even if it switches, you can still like calculate the control input for it, like query the control input for any point in time. Okay. All right. So yeah, I guess how do we find this this K of t? So we're gonna use a technique that's a variant of the LQR technique that we introduced a few lectures ago. So this is going to be called time varying LQR. So, okay. So yeah, again, given the setup from before, so the dynamics are x dot equals f of x u, some nominal trajectory x0 as a function of time, nominal control input u0 as a function of time for t in 0 to capital T. We're going to define a new variable, which is similar to what we had done in our original LQR discussion. So this variable x tilde of t is going to be the deviation of the actual state from the desired state. So we're just going to define this to be x of t, the state that your robot is actually in at time t, minus the state that you want to be in at time t, so the nominal state. So we can then differentiate this with respect to time. This is x dot of t minus x0 dot of t. So because x0 is changing with time, this term is not necessarily 0, right? This is some non-zero quantity. So x dot at time t is exactly f of x at time t, u at time t, and then I'm just going to rewrite this. So by definition, x at time t is x tilde plus x0. And the same thing with the control inputs. So u at time t, I'm going to, I guess I didn't define it here. Let me do it here. So u tilde at time t is u at time t minus u0 at time t. So this is u tilde plus u0. And then we still have this minus x0 dot at time t. So f is nonlinear, right? We're assuming you have some nonlinear dynamics like the planar quadrotor or the 3D quadrotor. So we can linearize these dynamics. Again, by doing a first order Taylor series expansion. So I can write this or approximate this using linearization as A, some matrix A at time t, x at time t minus x0 at time t plus some matrix B u at time t minus u0 at time t. So the only, I guess, difference here between this and what we have seen before with LQR is the matrices that define the linearization. Those are time varying because our dynamics here, the dynamics on x tilde are time varying because x0, the reference trajectory itself, the reference state is time varying. So I can write this more compactly then. So x minus x0 is x tilde. And then this is u tilde. Okay, and this is x tilde dot at time t. All right, so yeah, essentially the same as LQR. Our previous discussion of LQR, just with everything here being time varying because we're trying to track a trajectory. So yeah, I guess similar to our original LQR discussion, we can define a cost function, so a performance objective that we try to optimize using feedback control. Again, this is going to be essentially identical to what we had with LQR, just with things being time varying. So I'm going to define the cost function to be an integral from 0 to capital T. That's our time horizon on which the trajectory is defined, of x tilde t transpose q x tilde t plus u tilde transpose r u tilde dt. So yeah, this is identical to our previous LQR discussion. So this is the penalty for deviating in the state from the reference control input, the reference state. And this is the penalty for the control input deviating from the reference control input. And the Q and R matrices are user-defined that tell you exactly how to penalize deviations in different states. In principle, actually, these can also be chosen to be time varying. So I can write Q as a function of time, R as a function of time, if I wanted to. So maybe as time gets closer to capital T, I have a higher penalty on deviation in state. Like I really want to be close to the final state. In practice, you often choose these to be constants in time. Question?
Yeah, I kind of have a question about like the stability
Mhm.
like, of the like if you have a time varying system. So I know like usually we say like something converges to like a
Yeah.
but then how do you like prove that something like converges to like a trajectory?
Yep.
Time varying?
Yeah, very good. So we're actually not going to do that. In our original LQR discussion, we said that LQR gives you two things. One is like it optimizes this kind of performance objective, and it gives you asymptotic stability for the linear system. We're going to give up on the asymptotic stability part here, partly because asymptotic stability here isn't well defined, right? Like our kind of world ends like at capital T. Like we're not defining even the trajectory we want to be at after capital T. So we're not going to ask for asymptotic stability or any other kind of stability. We're just going to say this is our objective. And I think this has like fairly clear intuition, right? Like this is saying like don't deviate too much in state and don't deviate too much in control input. And we're just going to try to optimize this question.
If we no longer care about asymptotic stability,
Yeah.
What's the reason for our linearization?
Yeah, so the reason for the linearization is that we're going to be able to actually solve this optimization problem.
Could you solve it even without like the non-linear dynamics?
No, not in general. Yeah, so if you have just these dynamics over here, x dot equals f of xu, and you try to find a feedback controller that optimizes this objective, that's not something one can do, at least analytically, for a nonlinear system. So yeah, for a linear system, or linearized system, we can calculate a feedback controller that is going to optimize this objective. And yeah, it's basically almost identical to what we had done with LQR. So let me just write down the statements for the linearized dynamics. So time varying linear dynamics, we can calculate this gain matrix, which I wrote over here. So K of t, that will optimize, really minimize, I guess, the cost function. From any initial condition. So yeah, the way to think about this is if you choose some particular values for this matrix, this gain matrix, and that fixes your feedback controller. You can apply that feedback controller, so let's say this was the trajectory again. So from any initial state, like wherever you start off, you can apply this feedback controller. It's going to do something, right? If you just make up random numbers, it might like do this, like not even get you anywhere close to the trajectory you want to be at. If you choose a good feedback controller, it will kind of roughly get you back to the desired state. What I'm claiming is that I'm going to describe a procedure for calculating a particular k of t that's going to optimize this objective from any initial condition that you start off in. So for any initial condition, in principle, you can like run the feedback controller, calculate the states and control inputs that result from applying the feedback controller, and that quantity is just a scalar, right? Just a number given an initial condition. And this process that I'll describe will find you a gain matrix that optimizes that from any initial condition. So that's, yeah, it's basically exactly analogous to our original LQR discussion. So it's going to be, again, 2 steps. So let me write down step 1 first. So we're going to solve this Riccati equation, which we had solved in like LQR when we discussed it initially. It's going to be a slightly different version of the Riccati equation, so I'll write it down. It's Q. So yeah, sorry, these 2 terms are also on the right-hand side. So everything here is known. So Q of t, R of t, those are the matrices that define the cost function over there. A of t, B of t, those are the matrices that define your linear, time-varying linear dynamics that you get from the linearization process over there. Yeah, I guess the distinction between this equation and the previous version of the Riccati equation we had discussed when discussing LQR, one is that everything is time varying, right? The A and B matrices, potentially the Q and R matrices as well. The other big distinction is that the term over here, if you maybe go back a few lectures, look at this equation, this was a 0. So that was an algebraic equation. This is a differential equation in the variable s of t. So this is a matrix differential equation. Which sounds sort of complicated, but actually is not that complicated. So each element here, so S of t belongs to, so S of t is a matrix. So it's an n by n matrix for any point in time. So you can think of each element of S of t on the left-hand side, or S dot, I guess minus S dot on the left-hand side. Everything on the right-hand side, if you look at the dimensions, is also n by n. So Q of t is n by n. If you multiply out these matrices, you'll see that they're n by n. So for each element on the left-hand side and the right-hand side, you have a differential equation. So you have a system of n squared, so n by n differential equations. This is not analytically solvable, so we're not going to be able to write down some closed form solution for this, but we can integrate this, or we can solve this numerically. So for example, using ODE45 in MATLAB, if you use that, there's also SciPy dot integrate in Python. We need some boundary conditions here to solve the differential equations. And yeah, I guess typically what you do here is given some final value of S of t. So S at time capital T, you fix it to something that you choose. So for example, just the identity matrix, and then you solve this differential equation. This gives you S at every point in time. So it gives you a matrix at every point in time. And then the second step to actually get the feedback controller, I guess this step is relatively straightforward. So K of t, let me just get the signs correct. So K of t is R inverse B times S of t. And that's the optimal gain matrix. All right, so again, let me just pause for a second and just make sure the process is clear and what I'm claiming is clear. So the process is this two-step thing. You solve this differential equation, which looks a little bit ugly, but you're not solving it analytically. You just call OD45 or some other numerical integration technique. You get S at every time by solving this differential equation, and then the gain matrix is just this. You just multiply these matrices. Question?
When we solve that first equation,
Yeah.
one, you just replace all the t's for the end.
Sorry, say I want to replace all the.
Replace that like variable t with the end final goal.
For solving the differential equation, like you need some boundary condition, so either like at time 0 or at time capital T. Yeah, typically like you set the boundary condition at the final time, and then you integrate this equation sort of like backwards because it's like minus s dot of t. And yeah, what that will give you is s at every time that satisfies this differential equation. Does that make sense?
Yeah.
Okay, good. All right, other questions? Go.
So the F is versus S of big T equals S. Is that S final?
Yeah, as final. Yeah, good. So this is something that one would like specify. Typically, you just choose it to be the identity, or you choose it to be like Q or something like that. Like almost like any reasonable choice like works in practice. Yeah, often it's just the identity matrix. Good. Other questions? Okay. Yeah. Go ahead.
You said that should be chosen as any reasonable matrix, but what is the semantic meaning of S?
Yeah, so the semantic meaning is, okay, I guess I didn't discuss this here, but so if you remember from our LQR discussion, this S at time t has a physical meaning, and specifically it's like X transpose Sx is the cost to go. So at any, maybe I'll write it here. So if I give you some state like x tilde at time t, you take the transpose multiplied by s, multiply that by x again. So this is a n by n matrix. This is a n by 1. If you take the transpose, it's a 1 by n, so you get just a scalar. So it turns out that this scalar corresponds to, actually let me write it like, yeah, this is okay. Okay. So this scalar corresponds to the cost, which is this, that you would incur if you applied the feedback controller from this state.
So if it's a fewer identity makes sense.
Yeah, so the S at the final time is basically, it's sort of like a terminal cost. Like it's saying at the final time step, like what's the, it's just something that you define, right? Like what's the cost function for like the future. There is no future in a sense, right? Because we're saying like you don't have to like follow the trajectory after that. So you just essentially specify some like value like for the final S like at capital T. Yeah. All right. Good questions. Okay. Other questions? Go ahead.
How much does like choosing that to be something random affect your solution?
So random, I think if you make it very small maybe or like very large, then it might change the solution a bit. But yeah, I think typically, like I said, if you choose it to be the identity or if you choose it to just be the Q matrix, like that works pretty well. And it's not gonna be kind of dramatically different, at least in my experience. Yeah. Okay, so yeah, I guess the last thing I want to do is like show some of this stuff working in practice. Let me switch back. So yeah, I just want to show just a few videos. This is a very biased selection of videos. This is all from stuff that I have worked on in the past. This is an under-actuated double pendulum, so it's also called an acrobot. The interesting thing about this system is that it has 2 degrees of freedom. So there's a shoulder joint and there's an elbow joint. But there's only one actuator. So there's a single motor at the elbow joint and no actuation at the shoulder joint. And so yeah, you can, the goal here is to do what's being shown in the video. So using the single motor, you kind of swing up the pendulum and you try to balance it at the top. The reason it's called acrobat is because it sort of mimics a human acrobat, like from a high bar or whatever those are called. You don't have much control authority at the wrists, right? You can't apply much torque, but at the hip you can apply a lot of torque. This is also actually related to a model of walking known as the compass gate walker. So compass gate walker is like a drawing like compass. So if you think about the pendulum kind of in this like kind of configuration, there's no torque that you can, or not much torque that you can apply. So yeah, I guess it's this kind of configuration. There's not much torque that you can apply like at the ground, but there's a lot of torque that you can apply at the hip. So that's another kind of neat connection. So this trajectory was found using some of these motion planning or trajectory optimization techniques. So a nominal trajectory that goes from the downward configuration to the upward configuration. If you just apply that, this is like a sort of chaotic system that's going to wildly not follow the trajectory you specified. So we were using like exactly this technique that I described, time varying LQR, to make the system follow the desired trajectory. I think I saw a question.
You answered it.
Okay, all right. I guess what was the question?
Like where's the trajectory?
Okay, I see. Got it. Yeah. Yeah. Here's another example. This was with a fixed wing airplane that is trying to get through obstacles that are less than a wingspan away from each other. And this is exactly the same kind of technique. So we're assuming here that we know where the obstacles are. We plan a trajectory that makes the airplane avoid the obstacles if you were following it exactly. Of course, you're not going to be exactly following it. So again, we have a time-varying LQR controller that corrects for deviations from the desired trajectory. And then we crash into a net because the room wasn't that large. And yeah, I guess here's a final example. So this goes back to, sorry, let me just pause it here. This is me in grad school. So yeah, this goes back to a point that you made, which is when do you replan versus when do you follow some particular trajectory. This video is going to show an example of planning or replanning. Actually, it's just like planning here. Let me just play it for a bit. And I think this is explained. So the interesting in this setup is that the robot doesn't know exactly where the obstacles are until it leaves the launcher. So it comes off the launcher, and then there's some like system that says, okay, like here are some obstacles, and then it has to like instantaneously basically like plan to avoid the obstacles. So that clip over here is showing the setup. So the airplane doesn't know where the obstacles are, comes off the launcher, and then suddenly it's told, here are a bunch of obstacles, and then it needs to plan to avoid them. So what we were doing here was calculating a whole bunch of different trajectories with corresponding control inputs and corresponding feedback controllers. So you can think of this as a kind of library of trajectories with associated feedback controllers. There was an additional step here, which was calculating these blue kind of tube-like regions, funnel-like regions. I won't have time to go into that, but what we can guarantee here is that the robot is not going to leave these tubes if you apply your feedback controller. So what happens at runtime, so when the robot is told, like, here are a bunch of obstacles, it basically searches through this library of trajectories with associated tubes, and it tries to find one that's collision-free, so one that doesn't intersect the obstacles. If it finds one, then it executes that. And these are just different clips showing the different trajectories that are found with these associated tubes that the system is guaranteed to remain in if it applies the feedback controller. So yeah, the basic kind of architecture here is identical to what I described. So you plan or a bunch of trajectories, and then you have associated feedback controllers, actually exactly using time-varying LQR for their system. And then yeah, I guess I was bored one day, and then I was at MIT, so I made the obstacle spell at MIT, which I regret now. Every time I show that video, but anyways. Yeah, I guess questions on this. So this is just showing that this stuff like really works in practice, Mike.
So did you have like the funnels pre-loaded in
Yeah.
your library?
Yes.
So it was just like doing a search?
Yes, yeah, good question. Yeah, so the funnels were pre-computed. At runtime, you just search through them.
Okay.
All right, I'll see you next time.